So let's talk about directional derivative a little bit. Suppose you are interested in knowing how fast wind is moving from San Jose to San Francisco, or you're interested in knowing how fast the wind is moving from San Jose to Santa Cruz. So you are calculating the rate of change in different direction. So we're introducing directional derivative. Suppose you have a function. So suppose you have function f, let z be equals to f of x and y. The derivative of function z in the direction of vector. For example, suppose you have vector like v, let me use the unit vector. Then I'm going to talk about how to scale your vector. U, which is defined as a and b at point x sub 0, y sub 0 is defined this way. The directional derivative of function f at point x sub 0, y sub 0 in the direction of unit vector u is equal to the limit of f of x sub 0 plus at, comma, y sub 0. I need more space. And wrote down a little bit large, so it doesn't fit. The directional derivative of function f at point x sub 0, y sub 0 in the direction of unit vector u is equal to the limit of f of x sub 0 plus at and y sub 0 plus bt minus f of x sub 0, y sub 0 divided by t as t goes to 0. If this official limit, this is the official definition of directional derivative. If this limit exists, then we can use some shortcuts. The shortcut is the directional derivative of function f, x sub 0, y sub 0 in the direction of vector u can be written as, well, the partial derivative of function f of x at point x sub 0, y sub 0 times a plus partial derivative of f with respect to y at point x sub 0, y sub 0 times b. Okay. So I gave you two definitions. One of them is the limit definition. Remember that in elementary calculus, we start by introducing the limit definition of derivative. Then we said that, hey, for nice functions, if the limit exists, we can use some shortcuts. For example, find the directional derivative of function z, which is given to you, well, let's take a look at that function x cubed minus 3xy plus y to the 4th, 4y squared plus 4y squared when vector u for an angle theta equals to pi over 6. at the point. So the given point to you is 1 and 2. Okay, 1 and 2. Here we go. We're going back to elementary calculus. We have the angle and we want to drive the vector out of that angle. From elementary calculus, or even pre-calculus, vector v can be written as, well, cosine of pi over 6 and sine of pi over 6, right? So vector v is nothing but, here you have square root of 3 divided by 2 and a half. And this vector is a unit vector, definitely. The scale is just 1, so we're going to just use u representing the unit vector. Just a quick note for you. The magnitude of vector u is equal to square root of 3 divided by 4 plus 1/4, or just square root of, well, here you have 4 over 4 or 1. So u is a unit vector. There is no doubt there. Let's follow the formula. So the directional derivative of function f at the point 1 and 2 in the direction of vector u is equal to, when a partial derivative of f with respect to x at the given point 1 and 2. Partial derivative of function with respect to x is going to be 3x squared minus 3y, and then we're going to substitute 1 and 2. So I'm going to substitute 1 and 2 eventually, multiplied by a is square root of 3 divided by 2 plus partial derivative of f with respect to y, negative 3x plus 8y, and multiplied by a half. So now you need to substitute 1 and 2, 1 for x and 2 for y. So you get 1 squared and y is 2. And x is 1, y is 2. So let us simplify this more. The directional derivative of function f in the direction of vector u is equal to, here you have 3 minus 6, which is negative 3 times square root of 3 divided by 2, and here you have 16 minus 3 plus 13 divided by 2. If you want to get a correct value or approximation, numerical value, use a calculator. Perfect.